Gunnar Martinsson is going to be our second talk.
I can't remember what it stands for, but it's a method that tries to come up with a decision that works for user approximate that. I mean, yeah, if you have a round contour, for example, you just put down the space.
Right. Many thanks for the invitation. It's a great workshop. I wish I could stay longer, but it's great to be here. And I'm going to talk a little bit about these projection methods that Petros described yesterday in the overview. So the starting point here is a fairly, by now, well-established technique that I'm sure most of you in the room know. I'm going to describe it anyway because I don't want to assume that everybody has seen this. But so this is method that are based on randomized projections for computing a low-rank approximation to a matrix. And what we've been working on quite a bit the last few years is to see, can some of these ideas be used to compute full factorizations of matrices? So say you have a matrix that's, so in this case, the assumption is not that it's gigantic, but it's large enough that using existing methods would be challenging. So say tens of thousands, hundreds of thousands, maybe millions if you have a big computer. We want to compute a full factorization of it, or perhaps you want to compute a partial factorization where the rank, the numerical rank is not tiny compared to the matrix dimension. Say it's 10% of the matrix size or 50 or something like this. What do you do efficiently then? And some of these things will also lead to out-of-core implementations for really the basic low-rank approximation. Again, for the case where the rank is not that low. And some of the main themes here are how to use randomization to minimize communication. So the idea to get efficiency for most of these things is that we want to cast so all these algorithms, they spend a large number of flops. And flops have different costs. And the cheapest ones we know are pretty much, in this context, are matrix-matrix multiplications. So if I can take any of these matrix algorithms and I can cast it so that I spend the vast majority on processing large chunks of the matrix, then typically I get high performance. And this gets particularly important if you do things like GPU computing, if your matrix is stored on a hard drive, anything like this. So I should say here, when I say that an algorithm is blocked, then this is in contrast to matrices, to algorithms that proceed by a sequence of matrix vector operations. So classical column pivoted QR would be an archetypical one for that. Okay, so what I'm going to do is I'm going to start by just briefly reviewing this randomized SVD and then talk about how to generalize it to full. So the randomized SVD for the case when k is small, when the rank is small. So it is this algorithm, and I'll go a little bit fast because I'll assume that most of you have seen this, but some may not have. So the setup is this. I'm given a matrix A. It could be modest size. It might fit in RAM. It might not. It might be sparse. It might be dense. And the only assumption on the matrix is really that it has low numerical rank, that its singular values decay some sort of decay, so that it makes sense to approximate it by a rank K matrix, where K in this case is substantially smaller than the matrix dimensions. And I want to compute an approximate factorization where U and V are very thin matrices like this, D is a small diagonal matrix, and my objective is to have this product be close to A, so that the norm of the difference there is small, as opposed to having very high relative accuracy on all the eigenvectors or singular vectors or something like this. And the algorithm that we proposed for doing this looks like this. So you draw a tall, thin Gaussian random matrix, R. I multiply them together to form what we call a sampling matrix, Y, that's also tall and thin. So each column of Y is a random linear combination of the columns of A. And then the claim is that if you look at the space spanned by the columns of Y, then this forms a it captures the space spanned by the dominant left singular vectors of A. So it's a reasonably good basis for the column space of A, reasonably close to optimal, with one caveat, and it's that you need to draw a few extra vectors. And the key thing that comes out of both numerical experiments and out of the theory is that the number of oversampling you need to do is quite modest. If you draw 5 or 10 extra samples, then you already can, with very high probability, say that you're close to the optimal, at least for the case where the singular values decay reasonably fast. Okay, so that's the function of the sample matrix Y. So then what you do is you orthonormalize these columns. You have a set of spanning vectors, but they're typically clustered along the directions of the dominant singular vectors. So you need to orthonormalize them. You get an orthonormal basis. You then project the columns of A down to that basis. You get this matrix B, which now is shaped like this. I do a dense SVD of B, and then you just project back up. So this is the RSVD. So this is the starting point. This has been around for 15 years or something. So the question now is how, and I should say before I move on to the next case. So really one of the main advantages of this method is that you only interact with A through the matrix multiply. So this typically gives lower accuracy than a Krylov method would do.
I'm sorry, how do you measure accuracy in your context?
So for instance, the question is how good are the diagonal entries of D? How good approximations are they to the singular vectors? If I use the SVD as a low-rank approximation, how well does that compare to the space you would get by optimizing in the Krylov subspace? So in the Krylov subspace, if you start with a single vector, you can access, in this case, the kth power of A, which will...
But you don't measure angles, right? When you look at accuracy.
Right. So, I mean, so here, the purpose of this algorithm is just to minimize the norm between A, the difference between A and the product. Right. But certainly, if you can apply higher powers of A, you will do better on that metric. Basically, in regards to any question you might ask in terms of the quality, a Krylov method will do better than this. But if you keep fixed the number of matrix vector multiplies. But the point here is that all the interaction is through a matrix multiplied like this. And you can even reformulate this so that you only see the matrix once. You can sort of do both of these in a single pass of the matrix. So you don't need to store the matrix at all. So you can make it extremely communication efficient. And this is really the key to the high computational efficiency we've seen. So the question I want to talk about in this talk is, well, what if K is not much smaller? What if the rank is not much smaller than the sizes we dimensions? So you want all the singular values or something like this. Well, in principle, you could have, of course, just set K equal to N in this algorithm, but this would be kind of inane because then the matrix B would not be small anymore. It would be the same size as A, and you would have to solve exactly the same problem you set out to do. So the natural way to do this, the sort of most immediate extension of the randomized SVD to the case of computing a full matrix factorization, it appears, for instance, in a paper by Demo and Dimitri and Holtz from 2007, and it looks like this. So you draw, in this case, a square Gaussian matrix. So a square Gaussian matrix, you just orthonormalize its columns. And that forms your right factorization. So in this case, we're looking for I've made one softening of my requirements. So now I don't require the middle matrix here to be diagonal. I accept a triangular matrix in the middle. So U and V should be unitary. I allow a triangular matrix in the middle, but I still want it to be rank revealing in the sense that if I truncate this factorization to the K dominant terms, then that should give me a rank K approximation that's reasonably close to the optimal one. So that's the game I'm playing. I'm giving up on diagonality of the middle factor. And in that case, this is a very natural extension of the randomized SVD. So in this case, I get a square Gaussian matrix, I orthonormalize the columns, then I get sort of a hard distributed unitary matrix here. I use that as the right factor in the factorization, and then I just compute an unpivoted QR factorization of A times B. And this is it. So it's an extremely simple thing to compute. There are, I suppose there's only one matrix multiply and two unpivoted QR factorizations. Okay, so this is provably rank revealing as it turns out. You can work through the analysis and you start looking at, well, if I look at the first K columns of V, then that sort of looks like a tall thin Gaussian matrix. So the sort of first K columns of A times V, it sort of is like the matrix Y in the RSVD and so on. So for small k, it's very similar conceptually. And in some ways, it's a silly algorithm because it takes a lot of flops. But the key is that everything here is very, very fast on modern processors. So I think Demo's starting points in investigating these things was looking at things like Strassen matrix multiply. So there's, of course, these algorithms for computing two matrices that are faster than cubic complexity. And they showed that you can do this in a perfectly stable way. And then if you can do the matrix multiply fast, you can also do unpivoted QR factorization very fast and stably. And then the point here, but all the things you could easily do if you have Strassen, they do not reveal rank at all. It doesn't get you to the spectral structure of the matrix, but that is what this Gaussian matrix does. So if you introduce this randomization, then you get something that's provably rank revealing. And you can do it in complexity, whatever it is, 2.81 or something.
So is this rank revealing like the rank revealing Ming talked about with the singular values of the subblock?
So it's rank revealing in a very weak sense. Their theorem is very, very weak. It involves a gap in the spectrum, or I suppose Ming's did as well, but his estimates are much sharper. I'll show you numerical experiments that will illustrate the point. So in this talk, I don't use the technical definition of rank revealing. So there's this definition that the discrepancy between the exact singular value and the bounds you get should grow at most polynomially as the matrix size increases and this kind of stuff. That's not what I mean when I say rank revealing. I use the term in an informal sense. Okay, so this works fine. And it turns out that if you run this on a just modern computer, on a normal computer, it will run much faster than column pivoted QR, even though there are much more flops. So there is some interest to this method. And if you want to get better accuracy, you can do this slight modification that I'd be curious to see if somebody has seen this, because it's a very simple idea. I'm not at all claiming originality, but it turns out that if you just apply A a couple times to G before you do this algorithm, then you actually get extremely good rank revealing properties.
You're doing a power method there, right?
Yeah, it sort of is, yes, but combining it with the random matrix.
It's a square of G, right?
Yes. No, it's not a square of G, it's a square of A. So I apply...
G is a square matrix, right?
Yes, G is square, yes, I just misheard. Right, so in any case, and if you do this on a GPU, then this operation is free. Applying A to a square matrix costs nothing, basically.
Sorry, so A is a square, right? So you could have done A to the 2QG, but instead you're doing A transpose A.
So I don't assume that A is symmetric. If A is symmetric, right.
But you could have done A, since A is square, right? You could have taken 2Q powers of A.
Oh, it's square only for notational simplicity. It doesn't have to be square.
Because you want singular. I see.
Right, so the method works whether A is square or not. The squareness is purely for notational simplicity.
I understand.
Right. Okay, so let's look at how this works in practice. So here's a very simple example. So here I have a matrix whose singular values decay very fast. They decay exponentially fast. They go all the way down to double precision. And the two lines here are the bounds you get from this very simple randomized URV algorithm that I described. So when you do a rank revealing factorization, you get a triangular matrix. You want to say, so the k singular value of the top left, k by k block, provides one side bound. That's a lower bound for the k singular value. If you look at the larger singular value of the bottom right block, then that's the other one. So you get two estimates that sandwich the exact singular value. And in this case, it all looks very nice. But the point is that in this case, basically anything you do will work well. If you do column pivoted QR, it does even slightly better. It's slower actually, but it does a little bit better. And if you use just a couple steps of power iterations, you basically nail the singular values exactly. Here's a slightly more challenging example. The singular values decay more slowly. Here is this simplistic URV algorithm. That's column pivoted QR. And that's what you get if you just apply a couple of powers of A first.
Just understand the construction here. Okay, you control the spectrum. How do you use as left and right singular vectors? Random Gaussian, random orthogonal matrices? Or what's your construction of the input matrix here?
Oh, yes. So my test matrix is random, but it really doesn't matter in this case. It's basically rotational invariant. So it only depends on. Yeah.
When you plot relative errors for the small singular values, this looks nice because in the eyeball norm everything seems to bunch together. But when the singular values become small, what happens to the relative errors?
We'll return to that. So this is actually not the algorithm I'm proposing. This is a warm-up. It's a very simple example to illustrate the concepts. We'll look at relative errors in a little bit. So the column pivoted QR looks very different for other matrices. I'll show an example in a bit. For the randomized methods, it doesn't really matter. It's only the singular values. Okay, here's another example. It's the same story. Okay, so here's the method that I'm going to describe a method that can be interrupted, that's sort of much more similar to traditional methods that you've seen. So the first one was just a way of illustrating the concept. So what I want is I want a factorization where U and V are unitary. The middle matrix T should be triangular. In this case, I choose upper triangular. It's natural when the matrix looks like this, which is the case I'm looking at. And I want it to be rank revealing. So in particular, I want, as I said, truncations of this to be close to optimal rank K approximations. And I'm also going to be a little bit greedy. I'm going to want the diagonal elements of T to be very good approximations to the singular values of A. This sometimes happens, and it's very nice. In that case, you get a lot of stuff for free. So as an overview, what I'm going to describe, it's a blocked algorithm. So you choose the block size, which is purely a computational tuning parameter. If you run this on a computer like this, you should think of the block size as being maybe 100. If you do an out-of-core computation, you should think of it as being a couple thousands. If you do it on a big distributed machine, then God knows. It's a complicated optimization problem to pick the best block size. So the idea is I start with the matrix A, and now I'm going to behave just like textbook linear algebra text. You apply householder transformations. In this case, I'm applying them both from the left and the right. The ones I apply from the right, their function is to move as much of the weight as possible into the first columns. And then when I place as much weight as I can in the leftmost columns, then I just apply householder transformations from the left to make the matrix upper triangular. So you do this one after another. So this is exactly the pattern of, for instance, column pivoted QR, in which case you apply permutation matrices from the right. So that's more restrictive. And again, householder reflectors from the left, typically. Okay, but so the trick here, though, what's been an open question in numerical linear algebra for a long time, is how do you find groups of these transformations? There are many different ways of finding one vector at a time to do this, but how do you group them and find? And of course, this is exactly what the randomization is extremely good at. So let's be a little bit more precise. If we look at the first step in this cartoon that I did in the last one. So I have a block size B. So this is the first step. So I want to find two unitary matrices U and V. And I blocked them, so these are the first B columns, here are the first B columns of U. And this leads me to a matrix with a little B by B leading top left entry. So what I want to do here is I want to find U and V that squeeze as much mass as possible into T11. And then of whatever I couldn't get into T11, I want that to be located in T22. So T12 should ideally be 0. That would be very computationally expensive, so I tolerate, as long as it's small in magnitude, I'm fine with that. Okay, so the optimal choice would be to have, if I could hypothetically find a set of B vectors in V1 whose span exactly aligns with the span of the dominant left singular vectors of A, then everything would be perfect. In that case, I would precisely optimize here. T12 would be exactly 0, and everything would work beautifully. But this turns out to be exactly what the randomized SVD is very good at. So the key randomized step in the randomized SVD is to find a basis that almost aligns with the span of the top left singular vectors. So that's exactly what I'm doing. So in order to find this transformation matrix V, I do exactly as before. I draw a tall, thin Gaussian matrix. I apply A to it a couple times. So think of Q here as being either 0 or 1 or 2. It's not large. It's just a couple of applications of A. So I get my sample matrix Y. And then what I do is I just drive Y to upper triangular form. So I find the B householder transformations that drive Y to upper triangular form. And that forms my matrix V. So V here, it's a square unitary matrix, but it has a very compact representation. It's identity plus a rank B matrix. So it can be applied very rapidly, it can be stored efficiently, and so on. Okay, so this is basically the key idea. This is algorithmically we're done. Now it's just a matter of looking at how this works. Okay, so now, well, there's one slight twist that I haven't told you about. So actually what I'm doing is, in addition to this business of finding the householder vectors, I also compute a small SVD of the diagonal block and rotate this block accordingly. So that's just to really get the singular values on the diagonal. Because remember, the block size is fairly small. It's 100 or 1,000 or something. So computing a small exact SVD of that, it's basically for free. It costs you nothing, and it's very helpful. Okay, so this is the method. You get at the end, I'm just claiming, I'm going to show you numerical examples. You're not going to see any theorems. So this talk is it sort of proceeds in parallel with Ming's talk from yesterday, except that he was very rigorous with his theory. Here, there's no theory, but I'm telling you a little bit more about what happens algorithmically. Okay, so I'm going to end up getting the singular values on the diagonal, I claim, or very good approximations. Up here, I'm going to get non-zero entries, but they're going to be very small. They can be of size 10 to the minus 2, 10 to the minus 5, with just a very small number of power iterations. Okay, so let's look at this numerically. So here is a matrix, again, that has pretty fast decay of the singular values. So exponential decay, and it's an artificial matrix. I generated using this randomized technique. So I have compared to column pivoted QR, that's the magenta line. The green line is the method that Ming described where you apply column pivoted QR twice. So that turns out to improve things a lot. But it turns out to be fairly expensive unless you use the randomized column pivoted QR. Because column pivoted QR, it turns out to be very expensive in this context. So, and here we show relative errors. So basically, the UTV with no power iteration is essentially the same accuracy as Stewart's QOP algorithm, which is actually very good. For many purposes, that's perfectly good enough. And if you use a couple extra power iterations, you drive the error to be very small. And in this case, at least in this case, we have exponential decay. It does look like we're controlling the relative error very well. Here is a more challenging case. I have very slow decay of the singular values initially, then very fast, and then a nasty old tail that's going to pollute things. So this is sort of the nastiest example we see. And even here, it works very well. So you lose a little bit of accuracy right around this sharp drop-off. But for the most part, it works very well. Let me move. Here is the real example. This is a discretized boundary interval equation. So we see relatively slow decay of the singular values. And in this case, the randomized method behaves exactly as you would predict based on the examples you've seen. But the difference is that column pivoted QR now behaves very, very differently, because now the columns actually have specific meanings, and you sort of exhaust those sort of subspaces you can assign meaning to, and so on. So column pivoted QR behaves very differently, but the randomized methods are basically agnostic to.
So your errors are 10, 15, 20%, right?
But these are weird relative errors. This is sigma k plus 1 over some other sigma k plus 1.
Oh, they're spectral norms.
Well, they're sort of ratios.
Yes, I measure the error compared to the.
Sigma k plus 1, basically.
No,
That's what you have in the denominator.
It's this distance divided by the singular value. Yeah.
Okay, yeah.
Right. Okay, so the final numerical experiment I wanted to show was I claimed that the diagonal entries turn out to be good approximations to the singular values. Well, how good? So let's look at this. So this is with 2 steps of power iterations. I apply A transpose twice when I generate the matrices. And then the red line again are the singular values. The blue line, these are the diagonal entries you get from the column pivoted QR, which is some sort of proxy for the singular values, but it's known to be pretty bad. But Stewart's QLP algorithm is known to give fairly good approximations to the singular values in this regard. And it does much better, but the UTV is much better still. So you basically don't see the black line, which is the diagonal entries for the UTV, because it's exactly underneath the red one. Here is the challenging example. And now the black line sort of escapes a little bit right there, but they're pretty much spot on. And here's another couple examples. Let's look at computational timings. So I'll show you the exotic timings here. So this is on a 14-core machine, so we compare against the MKL implementations of LAPACK. So this is SVD, here is column pivoted QR, and this is UTV with 2 power iterations. So it's really much faster than even column pivoted QR. So usually column pivoted QR, it's oftentimes used as a poor man's SVD. You really want the SVD, you want to have rank revealing, but it's considered too expensive. But in this case, you can actually do something that's much faster and has the same advantage as column pivoted QR in that you can stop it. If you give it an accuracy, say you want to have 5% relative accuracy, then column pivoted QR has the beautiful property that you can just stop. You have the residual sitting there. You can stop. And UTV has exactly the same property. So this is for in-core, and then the thing that I really like about this slide, here's the matrix that's stored on a hard drive. And we maintain basically the same speed all the way up to 100,000 by 100,000 for a 14-core machine. So it's not, I'm not playing a trick that I'm using a very underpowered CPU. It's a very good CPU. And we can still feed it from the matrix that's stored on a hard drive. And again, you could stop this if you wanted to. Here is a distributed memory implementation, so 96 cores. We have SVD, we have column pivoted QR, and this is UTV, and I compare, just like Ming did yesterday, so sort of the gold standard here is unpivoted QR. So this parallelizes very well, and it's often used as a reference. It's not quite as easy as matrix-matrix multiply, that's sort of considered a cheat, but unpivoted QR is sort of the best you could hope for any non-trivial numerical algorithm. And we're getting reasonably close to that. Here is on a GPU. So we're comparing against state-of-the-art implementations of SVD. And that's column pivoted QR. And this is very frustrating to me, because if I'd shown this slide 9 months ago, then column pivoted QR at that point was up here. So it's a very iffy business to be in, because it's extremely dependent on, if you have high quality programmers who can put in a lot of time, then these things can change. And most of these examples, some of them are done by a collaborator of mine in Spain. And I mean, he's very good, but it's just him. It's not a big team. It's just one guy who has a little bit of time here and there. And some of them are done by my graduate student who has no formal training in HPC. So it's a very simple algorithm to implement. So this is the GPU implementation. And in particular here, I want to point out that there's basically no difference in applying higher powers, because applying A turns out to be basically for free on a GPU. It's absurdly cheap. So you can get very high accuracy out of this method. Okay, I think, well, we are at noon, but I think we started a few minutes late.
So
yeah, okay. Sorry, if somebody needs to sneak off, I won't take offense. But I just wanted to mention that the same ideas can be applied to do column pivoted QR as well. So I've sort of been saying a few times that column pivoted QR is slow, UTV is fast. It turns out to not be quite true anymore. It was true 3 years ago, but we figured out how to do block pivoting using randomization as well. And these ideas, they're so similar to the UTV that I think even with just a couple of minutes, I can get the main idea across. So the idea is basically the same. So I want to block an algorithm that drives a matrix to upper triangular form in such a way that it's sort of rank revealing. I want to have the first set of k columns be a reasonably good basis for the column space. So the traditional method here is to do column pivoting. You pick the largest column, you put it on the first, you orthonormalize everything with respect to that one, you pick the largest one that remains. And the problem there is that it's really inherently a sequence of matrix vector operations. And a lot of effort has been put into trying to block this. And I'll show you how it can be blocked. So again, looking at the first step. So how do you find a bunch of pivot vectors? Say you want to find 100 pivot vectors at once. So this is exactly this problem that comes up in CUR. It's finding the best subset of vectors to form a basis. And the algorithm that we have found works very well is a randomized one. So you take A, and in this case I used my random matrix like this. I project the rows down. I form random linear combinations of the rows of A to form a sampling matrix Y. And then I apply just basic column pivoted QR to the columns of Y. And Y is very small. So you pick B here to be small enough that Y fits in cache. So you can do these very communication-intensive things on Y. So I apply column pivoted QR to Y, and then that picks columns that turn out to be extremely good pivoting columns. And here, there's a very funny thing. So the randomization, it turns out to be very reliable when the singular values decay rapidly. In that case, you get very accurate Y. The dependencies between the columns of Y are very similar to the dependencies between the columns of A. But the randomization turns out to be very unreliable in the case where the singular values are flat. In that case, you're basically picking random pivot columns. They have no relationship to the pivot columns you would pick from A, but in that case, it doesn't matter. Any columns are good pivot columns in that case. In a regime where the spectrum is flat. So these are the two extremal points. You have one point where the randomization messes up with everything, but in that case, it doesn't matter. Any choice is good. And the other one, choosing the right ones is critical, but the randomization almost surely makes you find the right one. And then what I've been trying to prove, and I think Ming has been much more successful at this, is that you can sort of interpolate very nicely between these two, that nothing bad happens in the intermediate regime. All right, so that's how it works. This is the speed-ups we're getting against MKL. This is on between 1 and 14 cores. We're about a factor of 5 faster. And as matrices gets larger, as you add cores, things seem to be moving in our direction, so I'm very optimistic about this. And Ming and Julian Langu and a number of people are looking at working this into LAPAC. So this was, yeah. And here is an implementation of a GPU. And just illustrates the difference between working on a hard drive and a solid-state drive. So the advent of solid-state drives is very advantageous to us in this environment because they behave in exactly the ways we need them to behave to get high performance. Okay, this is just my last little cartoon. So it used to be, for purposes of low-rank approximation, you had a choice between SVD, which was optimal but very expensive, column pivoted QR. Now we have randomized column pivoted QR, which has basically exactly the same quality as column pivoted QR, but it's much faster. And we have this algorithm RandUTV that combines really the best properties of everything, I would say. So in many cases, in data sciences, remember that the off-diagonal entries are of size 10 to the minus 5 or something. So it really doesn't matter. The output is basically an SVD for many practical purposes. And yeah, here are some papers, some references. We have code. So this is multi-core. The outer core and the GPU implementations are not quite ready to be shared. That's work in progress. But the multi-core ones are all done. So thank you very much for your attention.
Do we have one or two really quick questions before we go to lunch?
Have you tried the UTV for sparse matrices too?
Yes. So in some, so as long as the rank, so when you apply this to a sparse matrix, then we have to be in the regime where the rank is much smaller because the U and V vectors will be dense. So it really only makes sense when the rank is small. And in that case, everything works the same, except you don't apply the updates to the matrix. So you can do those implicitly. So there's, if you, in the lingo of linear algebra, you have left-looking and right-looking algorithms, whether you actually explicitly update the columns, whether you postpone them. So if you have a sparse matrix, just don't do the updating of A. And everything works fine. But of course, U and V will be dense. So at some point, it's going to start to get expensive.
Yeah, go ahead.
So I assume you're getting very high accuracy convergence on this, but if you start getting lower accuracy convergence, can you get more runtimes? Is there a way to trade off in the other way?
Right, so in this case, the parameter, so there are two parameters that go in. One is the block size, which is a performance parameter. The other one is how many power iterations you apply. And that one, we don't do it adaptively. You tell in advance, and it's really based on how much accuracy do you want. You have some sense of how fast the singular values decay. And basically, if you try 2 and you find that's not accurate enough, or if you start with 0 and you find that's not accurate enough, you just have to redo it. I don't have a clever way of sort of detecting, oh, I picked Q a little too small, maybe I should go back, and I can reuse things. I'm guessing you can be much more clever about these things, but we haven't gotten there yet.
Okay, let's have the speaker again.